We're going to start our study of energy concepts. Energy concepts are so important, both just in straight up physics and in engineering. We're constantly accounting for energy relationships in various physical systems. And so what I want to do in this video is just kind of lay a conceptual groundwork to give us some terminology and get us set up for the bigger picture. And then we're going to focus in on specific pieces of the bigger picture in the videos that are ahead and start learning how to account for energy relationships in the context of physical systems. So let's talk about energy for just a moment, okay? Now, you know that there are a lot of types of energy that we talk about in everyday life. For example, we talk sometimes about chemical energy. And what chemical energy is, it's just simply energy that's stored in chemical bonds that can be released. So, for example, an exothermic reaction, such as, heating up the tip of a matchstick, that creates fire. It creates a release of energy, and where that energy is coming from is in the chemical bonds that make up the tip of the matchstick. So we have chemical energy. We also have what we call thermal energy. Thermal energy is really the energy that arises from the random motion of molecules and atoms in a substance. It's the type of energy that creates heat. And so, here's an extreme example of some sort of metal being smelted and heated up. But you know that if you were close to that, you could literally feel the heat energy coming off of it. And that's because that energy is coming from the fact that the molecules that both make up the container and the material substance that's melted on the inside, they're vibrating really quickly, okay? And they're transferring heat energy. And so a lot of times you'll hear thermal energy referred to as heat energy, okay? We sometimes talk about things like radiant energy. This is just the energy that's contained in electromagnetic radiation. We depend on radiant energy for life. That radiant energy comes from the sun, and that's being carried to us in the form of electromagnetic waves all across the spectrum, not just visible light, but the full spectrum of electromagnetic radiation. And that energy comes and hits the earth, and it heats us up and provides energy. So, those are three kind of basic forms of energy that you'll hear discussed from time to time. And then there are two other types of energy that we're really going to be focusing on more than anything. One is what we call kinetic energy. Kinetic energy, you can think of it as just simply being the energy that's associated with the motion of an object. So I have a bicyclist here riding her bike. She's moving, and by virtue of the fact that she's moving, she has kinetic energy. So anytime you're driving your car down the road, as long as it's moving, it's got kinetic energy. If you're walking down the sidewalk, you have kinetic energy. So anytime you think about an object being in motion, you need to understand that there is a kinetic energy that is associated with that motion. And then, of course, we have what we call potential energy. And you may have heard of potential energy. Potential energy is really an energy that's based on an object's position. It's potential because it's available to make kinetic energy, to create energy of motion, but it's not being used for that purpose. And so an example would be a stretched spring, okay? This is what this picture is showing. I've got a spring here and some masses that are attached to the bottom of it. And the result is that it has stretched that spring out. And now that spring is storing potential energy. If I were to take these masses off, then that spring is going to snap back to its normal length. And that potential energy is going to go into kinetic energy, right? So those are various types of energy that we can encounter. There are others. I don't want to just make a list of every type, but just getting you to realize that when we talk about energy, there is a plethora of types of energy that we can discuss given any situation. Now, like I said, what we're going to be focusing on right now is kinetic energy and potential energy. These two things together make up what we call the mechanical energy of a system. Whenever you hear the word mechanical energy, take that to be code for the total amount of kinetic energy, add it to the total amount of potential energy. So kinetic energy, potential energy, that's our focus. They make up the total mechanical energy of a system. Now, what I want to do here is I'm trying to provide a large picture concept. And where energy gets really interesting is when we consider how energy transforms and increases and decreases, because it's understanding those principles of how that operates that allows us to use energy concepts to make predictions about where a physical system is headed in terms of the positions of the objects, the speeds of the objects, things like that. So let's turn just for a minute then and just think about how energy can transform in a system. So let's imagine we have a system of particles. Now, you know that a system is just defined by being the set of objects that we're interested in. A system can consist of one object, or it can consist of a multitude of objects. And so what I've drawn here is a system of several objects, quite a few. And they're all doing their own thing. They're moving. Maybe they're interacting with each other. Maybe there's some charge on some of these that's causing certain particles to be attracted to each other electrically. Maybe there's gravitational forces attracting some of the particles. But this is a system of particles that maybe we're interested in. And we want to be able to look at those particles and kind of predict how's the system going to evolve over time. And energy concepts are one of the things that can help us understand that. Now, we need to understand that within any system, there can be all kinds of energy present in that system. You know, this can contain kinetic energy. Well, it has kinetic energy because it's moving. It can contain potential energy that arises from forces of interaction between those particles. There could be thermal energy in the individual particles. Maybe the molecules in each particle are vibrating and creating heat, all right? And of course, there's chemical energy in the bonds that make up those particles. So if we were to talk about the total energy in a system, we have to account for the fact that there could be all kinds of energy in that system, right? Kinetic, potential, thermal, chemical, all of those could be there. Now, the fact is that the energy in that system, those various forms, can actually jump from one form to another. And so we can have transformations of the energy within the system. Kinetic energy could be converted to potential energy. Chemical energy could be converted into kinetic energy, or thermal energy could be converted into kinetic energy. There's all kinds of possible ways that the total energy of that system can transform from one form to another. And the process doesn't have to just be one direction. It can go both ways. So kinetic can go to potential, but maybe the potential later goes back into kinetic, okay? So now the thing is, though, that even though those energy transformations can happen, what we have to understand is that in a closed system, say in a system that's not interacting with anything else, the total amount of energy itself can't change. So while you may have transformations from one form to another, if you were to add up the energy associated with each type, at any given moment, that's always going to equal the same value. And so that's where we say energy is conserved. The total amount of energy doesn't vary. But now the fact of the matter is that most systems are in contact with their environment. And it turns out that the environment can change the energy of the system depending on how it's interacting with that system. You know, it can add energy to the system by injecting thermal energy into it, right? So imagine that this system was in contact with something in the environment that was at a higher temperature. Well, you know that heat energy flows from hot to cold, right? So if the system is cooler than the environment that's around it, then some of that heat energy in the environment is going to start to seep into the energy of the system, so the energy of the system would start to increase. Another thing that can happen is that there can be objects in the environment that are exerting forces on things inside the system. And that's where we get work from. The best definition of work's done on a system when something in the environment is just exerting some sort of force on it. And that force can increase the energy of the system or it could decrease the energy of the system. And so we need to account for the fact that our system is contained in an environment. And sometimes we need to ask ourselves, well, is the environment pumping heat into the system? Or is the environment doing work on the system by exerting forces on it? Because if that's the case, then the energy of our system won't be conserved anymore, okay? Only a closed system that's insulated from the environment has the total amount of energy staying the same. But a system that's in contact with the environment, the energy that's in that system doesn't have to be conserved. And of course, this isn't just a one-way process. Just like the environment can act on the system can also act on the environment. And so maybe the system's actually warmer than the environment is. And so that means heat energy in the system is going to seep out into the environment. And so that's going to lower the overall energy of the system. And it's also possible for the system to be doing work on objects in the environment, right? That's not just a one-way process. It's not like that only the environment can do work. The system can do work as well and exert forces on objects that are outside of it. And so they can lose energy to the system that way. And so this is kind of the general picture. I mean, energy relationships, the large picture can look very complicated because you got all these transformations going on. You've got all this injection of energy coming in, all this loss of energy that could potentially be going out. And so that's why this one diagram in your textbook is so important, because this is the big picture. All right. This is straight out of your text. We have our system here, and it has an energy that's called the energy of the system, right? And that energy can be contained in any of these forms. All right. And those forms could be transforming back and forth into each other. So you can have transformations. Okay. And so now those transformations don't change the energy of the system, but they do mean that the kinetic, thermal, chemical, and potential can be changing at any given moment, just so long as that energy is going somewhere else. But we also have the environment that we have to take into account. And so we've got heat and work that can come from the environment and go into the system, or we've got heat and work that the system can do on the environment. This will add energy. This will remove energy. Okay? So the picture on the surface of it, just looking at all these potential transformations and additions and subtractions, that can seem kind of complicated. So what we need to do is we need to develop a way to account for each of those so that it's not complicated, so that we can actually say, okay, here's what's going to happen inside this system that's in contact with this specific environment. And we can keep up with those energy relationships and know where everything is headed. Okay, so the whole purpose of this video, I just want to introduce you conceptually to the fact that we have various types of energy, that we've got to think about our systems, that energy in the system can transform, and that the overall amount of energy of the system can increase or decrease depending on how it's interacting with its environment. And what we're going to start doing in the next video is putting some mathematical tools together to help us understand how energy is going to change in a system. Okay.